Welcome to week 10 of this NPTEL course on coherence and quantum entanglement. In the previous week, we had started with one problem of week 9 itself on spatial two-photon wave function, but we could not complete it last time due to shortage of time. So we will now start with that particular problem. We will complete that problem and then we will move ahead with week 10 problems. So just to give you the context, this was problem number 3 from last week. We were at problem B. We had done A, we were at B, and then we are supposed to do C and D as well. So before starting, let me just recapitulate. Let me read out this problem 3 for you. So this is the spatial two-photon wave function, the setup. So we have this PDC crystal and then we have two detectors, DS and DI. So the question is, let us consider the production of entangled photons using parametric down conversion as described in the figure. The expression for the two-photon state is given by this particular expression for psi Tp. Part A says, within the assumption of collinear down conversion and paraxial approximation, show that the electric field operators at the two detectors are given by this following expressions. Part B was what we were doing, and it says, next take Ks approximately equals Ki approximately equals K naught by 2, where K naught is the central wave vector magnitude of the pump field. And consider the one-dimensional version of this problem so that rho goes to x. Also, take the pump to be a completely spatially coherent Gaussian beam. The expression is given as follows, where omega naught is the pump beam waist. Show that the two-photon probability amplitude psi Tp, which is given by this expression, reduces to the following, which has 3 exponential terms, where omega z is the beam waist of the pump at a given z location and A is a z dependent constant. So we were doing this part B. Part C and part D are dependent on the result of part D. In fact, part B depends on part A, so everything is interconnected in all these parts. Part C says, finally show that the two-photon coincidence probability to within an overall z-dependent constant is given by this RSI, which is mod psi Tp squared. And part D says, plot the above two-photon coincidence probability R and describe it. So take about a few minutes to just go through this once and just to revise what we did last time, and then we will discuss. Okay, so let us now discuss. Let me quickly go over part A. So field operators at detector They were given by this expression over here. Then we made use of paraxial approximation, where that approximation comes into play at this step. Why? Because we assume that Q is much less than magnitude of Ks. This is the paraxial approximation. This means that the x and y extent of the wave vector is negligible and it is largely along the z direction. And using that, we came up with the final expression for the field operators at the detector. Now we will make use of these field operators to find the 2-photon wave function. So this is the expression that we are given, and this is for 1D. So we replace rho with x and q with kx. So 1D means we are replacing rho with x and q with qx. Sorry, k with simply ksx, the x component, which is essentially qx. Sorry, q we are replacing with kx. Pardon me. Q, of course, because this k has xy component and then the z component. So 1D would mean that out of this x and y, we just pick up this x component. Sorry, what's happening? Why am I not able to change? Yeah. So for 1D, we will only consider this x component. 2D would mean x and y both. So here in this q, we are replacing qs, we replace with ksx, and qi we replace with kix, which is just qx essentially. So q goes to kx, ksx. Sorry, I need to change my pen again, which is essentially qsx. Now this field operator we get from part A. Again we replace q with ksx and rho with xs, as you can see from here and here, and even this, the integral. Now this is already given to us and we need to find this out, find the expression for this. And we know the operation of the annihilation operator. So this is the action of the annihilation operator. It gives you a delta function and the vacuum state. So this delta function is 1 if ksx prime and ksx are the same. If not, it is 0. Now we will finally put this action of the annihilation operator and make use of it to get this expression. So here we are just writing down this expression and expanding by making use of the field operators. So this is the field operator for EI and this is the field operator for ES, the idler and the signal field operators at the detectors. And then this is psi TP that is given to us. So let me just highlight the thing so that you come to know what is what. So this part right here, is this and this is basically this. And finally we have psi tp. Let me see if I have a different color. Let me try this color, maybe. This maybe, let's try. So, oh, sorry. I don't know what's happening, why the color is not changing. Yeah, now it has changed. So this term over here is psi tp. And of course this projection onto this vacuum is as it is. Okay, so then what we do is we just expand it. We make use of this delta function or operation of the annihilation operator. So what that does is it basically makes this kix prime equals ksx prime equals ksx. This delta function will give you, when you integrate, upon integration it will give you this. So that's what is happening. Kix prime is replaced with kix and ksx prime is becoming ksx. And we already had this integral over dksx, dkix, and this ksx prime also becomes ksx. So this ksx over here and this kix prime becomes kix, this kix over here. So this comes from that integral of delta function and this comes from the signal integral over delta function. Same here also. Now we just put in the expression for this pump field, which is a Gaussian, and then we wrote down the separate terms for dksx and dkix integrals. So this is the integral for dksx terms and this is for dkix terms. Of course there is this common term which has ksx, kix both. Then we will look at the first integral. We will make use of this Gaussian integral, which is very important. You should remember this. We have made use of this integral multiple times and we will continue to use this integral all throughout in physics. So by using this Gaussian integral, the first integral, which is the ksx part, that reduces to the following expression after simplification, and then we will put this back again in this expression. So after substituting, then we are left with this kix integral, and we have made this particular substitution for alpha. Now once again we will make use of the Gaussian integral to evaluate the Kix integral. And after making use of the Gaussian integral, we have the expression for psi dp, which is as follows. Now this is the expression for psi dp, and everything that we will do now is just a simplification. So this is the final result that we have, means not really the final result, but this is the expression for psi dp. And now we will just make some substitutions and some simplification to get to the final expression in the form of these particular exponentials that is given to us. Okay, so let's just see what simplification we have made. So here we just opened up this bracket, then we took the denominator common, and then we took this exponential common. This exponential we took common inside with this exponential. Then we replaced this term with a z dependent amplitude. This is the z dependent amplitude. And alpha we know is this, so now we are just putting it inside this, and we want to look at this term inside this exponential because rest everything else is sorted. So we just need to look at the term inside the exponential. So we have replaced alpha with this substitution that we had made earlier over here. So just putting in that alpha, taking common numerator denominator, and then we got this. Then opening up the brackets, we get this. Then we do rationalization by multiplying with the complex conjugate of this term in the denominator, and this is where we come. Now the next step is we will make use of this particular identity. So the cross terms will cancel out, and then we'll be left with this sum of squares. So by making use of this this term inside exponential, okay, let me just write it in the next page because it will get too much cluttered here. So this part, then here this is what we will make the substitution for, this part and this part. Now let us group together the terms of square of sum and square of difference. Group together terms of this type and terms of this type. Now we will look at this xi term and replace that with also a square of sum and square of difference type of terms. So now this exponential term will become the following. let us look at the real coefficient. So real coefficient of xs plus xi squared, let me highlight. So real part we want to look. So this is the real part, and then here also we will have this as the real part with this part. Sorry, I forgot this to copy this omega naught squared term, and this mistake I made in the beginning over here. Wait, still something is wrong. K naught squared omega naught squared it should be. Yeah, K naught squared omega naught squared. See? This 2 into 2 divided by 4 cancels out, giving just 1. And then the denominator. Now this term cancels out with this term, and then 2z cancels out with this to give 4. And this is omega squared z is coming because we are given the expression for omega z. So this is the real coefficient of xs plus xi squared. Now let us look at the imaginary coefficient. Now imaginary coefficient, let me highlight, is this part here and then this part along with this prefactor. So let's write down. Now again these two terms in the numerator cancel out. Now -4 cancels with -8 to give 2. One term from the numerator z and denominator, they cancel. Again we'll bring in omega z. So this term is the numerator of this omega squared z and then getting k naught square omega naught square, that makes it what we want, and then 1 k naught will cancel, finally giving the following. Now let us look at coefficient of this difference term. So this difference term is over here and over here, this along with the prefactor term, this. So let's write it down. Now let us open up the brackets. Now this term cancels with this in the numerator, and negative cancels from the negative in the denominator. This gives us the following. Now this term cancels from numerator denominator, giving us very simple expression I k naught over 8z. Now let us put it all together. So we have simplified this exponential term by looking at the real imaginary coefficients of xs plus xi squared, and then the entire term xs minus xi squared. So real part of xs plus xi squared then the imaginary part and then the xs minus xi part. And this is precisely what we wanted to show. This expression over here, this a is a z dependent amplitude that we are representing with a prime z. So I hope this is clear. Just take about a few minutes to digest. Then we will move to part C. Just check all these steps once. Okay, so let us now proceed to part C. Part C is show that the two photon coincidence probability to within an overall Z dependent constant is given by this expression for RSI, and this reduces to this following: A exponential minus xs plus xi whole square divided by 2 omega squared Z. Okay, so this is very simple. We will just make use of this expression that we derived in part B. So this is already given to us. This is the definition. Now let us introduce this terms like this. This is identity. We will introduce this. So this is nothing but the psi TP dagger, and this is psi TP. This is because dagger, here it is just star complex conjugate. This is because we were already given this expression for psi TP over here, this right here. So this is psi TP and this is just the complex conjugate. So this is mod psi TP squared, and psi TP we have already derived over here. Sorry, there is a K naught here. So only this term survives. The rest are having exponential iota kind of terms, so they will just cancel and become 1. So this is what we get, the desired result. And this came from B. We made use of the result from B. Next, part D. So part D says plot the above two photon coincidence probability and describe it. So let us first describe it, then we will plot. So from C we have this. Now here xs tilde and xi tilde are dimensionless and they are defined as follows. And what we can note from this exponential is that if signal is at x, then idler will be at negative x and it will have a width of omega z. So maximum probability of idler will be at minus x if signal is at x, and it can be found within a spread of omega z centered around minus x. That is what this Gaussian is, and now we will look at the Mathematica simulation for the same. So we will look at the Mathematica simulation and for the plot, and this basically will complete the section that we were left with from the last class. So this will complete the week 9 problems, and then we can proceed to week 10 problem set. First, let me open up my Mathematica window. So here I have opened up my Mathematica window, and this is the plot. Let me execute it once again. Yeah, so this is the plot that we have, and the x-axis is xs. Okay, let me label it, and it is xs tilde. So let me put in this t, and let me put label. I forgot the syntax for label, but I believe yeah, it's axis label. I think this should work. Oh, it did not. Where is the label? Oh, Is the inverted quotes not required? Let me see then how to label. Labels, okay, here. Frame left, XIT, and bottom, XST. Yeah, now it is working. Okay, fine. So look at this part over here, and this is R top. Let me put R XS XI. Right, so let me do it. Yeah, so this is the label. I see frame label it is supposed to be instead of axis label. Fine. So this is the plot for our XSXI, the two photon coincidence count probability. And as you can see, this is in the form of this anti-diagonal. And why anti-diagonal? Because as we showed, if signal is at location x, let's say if signal is at location x, which is x equal to 2, then idler is at location minus x, which is minus 2, and it has this particular width or spread it has, which is proportional to omega z. And here, since we are in these normalized coordinates, that width is basically proportional to this half. Sorry, this 2. So half is in it's 0.5, so it is 2. So this width is of magnitude 2, and you can see clearly it is roughly like 2. Means if you see from here 0 to about 2, that's the width. So that's that. And similarly, if signal is at location, let's say minus 1, let's say over here, then idler has location plus 1. Okay, what is this? Can I mark? Oh, sorry, something went wrong. Yeah, fine. Can I plot a point on this? Is there something? Let me see. There is something called mathematics plot point. What if I do something like, let me copy. Okay, this is not working. This is throwing up some errors. Clearly, this is not the right way, it seems. Okay, there's something called list density plot. Oh, sorry, wait. Even in density plot, I think I'm messing up my brackets. This should be here and this. This should probably work. I don't know what's happening. Anyway, what I wanted to just show is if this point is at 2, signal at 2, then idler value is minus 2. That is what I wanted to show by putting a point over there, but seems like I'm not able to do that. Anyway, that should not be important. So this is the plot. I think we are done. Okay, so now that we are done with the week 9 problem set, let us get started with the week 10 problem set. So this is the first problem, again on the spatial 2-photon wave function and spatial 2-photon interference. It's a pretty long question which has got a lot of parts, 6 parts to be precise, up A to F. So let me first read out this question. The scheme below represents a spatial 2-qubit state S1 and S2 and I1 and I2. So S1, the one is little bit, S1 and S2 and I1 and I2, forming the two-dimensional orthonormal bases for the signal and idler photons respectively, where S1 represents the state of the signal photon passing through the hole located at the transverse position rho S1. So this is the setup. Let me read and then I'll explain the setup. So S1 represents the state of the signal photon passing through the hole located at transverse position rho S1, etc. The four-dimensional basis set for the 2-qubit state can then be represented by S1I1, S1I2, S2I1 and S2I2, where S1I1 represents the joint state of the signal and idler photons when the signal photon passes through the hole located at rho S1 and the idler photon passes through the hole located at rho I1, etc. Assuming that the probabilities of states S1I2 and S2I1 are negligibly small, we write the density matrix rho qubit of the 2-qubit state thus prepared as follows. The coincidence count rate at the detector is given by this expression. This is for spatial. And then we have the question parts. So let me first explain this setup. So what it is, we have the PDC source and this gives out signal and idler photons, and then we have this 4-hole interference setup and then the two detectors DS and DI. Now what is happening is that if the signal photon, let me highlight, if the signal photon goes through hole RS1, then the idler photon will go through hole RI1. This is what we are looking at, and this is the joint probability S1I1. So this is the S1I1 joint probability. Signal passing through hole located at rho S1 and idler through hole at rho I1. Then the other possible alternative is if the signal goes through hole at RS2, then the idler goes through the hole at RI2. And the cross type term, that if signal goes through RS1 then idler goes through RI2, that is not considered. So that is negligible, that we are showing, that we are assuming. So this is the setup, and in this situation the density matrix is given as follows and the coincidence count rate is defined with this particular expression. Now let us read the questions. Part A. What is the meaning of the diagonal terms of the density matrix rho qubit? So this is the density matrix. What do the diagonal elements mean? Explain why A and B should be proportional to the two photon spectral densities, that is A equals K1 squared S rho 1Z and B equals K2 squared S rho 2Z. So these are the A and B terms. Part B. What is the meaning of the off-diagonal terms of the density matrix rho qubit? Explain why C equal to D star should be proportional to the two photon cross spectral density, that is C equals D star equals K1 K2 W rho 1 rho 2 Z. Part C. Calculate the concurrence of the above 2-qubit state. Part D. Find the visibility V of the two photon fringes and show that V equals C. Part E. What is C when A equals B and mod C equals mod D equals half? What is the necessary physical condition for ensuring this? And part F. What is C when A equals B and mod C equals mod D equals 0? What is the necessary physical condition for ensuring this? So all these parts are there to this, and just go through this for a few minutes and then we will solve. Okay, so let us now look at the solution. Let us begin with part A. So part A is, what is the meaning of the diagonal terms in the density matrix, and explain why A and B should be proportional to the two photon spectral densities. So diagonal terms are probabilities of the two photons being found in the interfering alternatives. And what we know is that S2 rho Z is the spectral density, and K1 squared S rho 1 Z. Okay, this is getting too much cluttered. Let me this term represents the probability of being in alternative 1 So, K1 squared S2 rho 1 Z represents the probability of the two photons being in alternative 1. Alternative 1 is this highlighted in yellow. Alternative 1 means signal goes through rho S1, idler goes through rho I1. So the photons are located at rho s1 and rho i1. And for the given problem, the qubits that we have, so this qubit actually defines the spatial locations of photons, and thus A and B are proportional to S2, which is the spectral density. And so A is k1 squared S2 rho 1 Z, and B is k2 squared S2 rho 2 Z. So these are like more of descriptive type questions. Next part. This part is about the same question but for off diagonal terms. What is the meaning of off diagonal terms of the density matrix? And then we need to explain why C equals T star equals K1 K2 W rho 1 rho 2 Z. So off diagonal terms represent coherence. Coherence between the alternatives. Also, the correlations are determined by the cross spectral density W. Correlations or coherence. So therefore we have C equals T star equals K1 K2 W rho 1 rho 2 Z. Now you may ask that in this expression we have 2 K1 K2 W. So this whole thing is actually, if you combine this whole thing, this is W rho 1 rho 2 Z. So since we have twice of this term, you might ask why not have twice, and or where did the factor of 2 go? So that's because we have 2 K1 K2 W2 in the expression, and this is equally distributed between C and D. So equal contributions from C and D, K1, K2 from W from C, K1, K2, W from D, that will add up and give you 2 K1, K2, W2. Okay, so now we can move to the next part. Calculate the concurrence. So we need to find out now concurrence, which is a measure of entanglement. So this is the definition of concurrence. Where these lambda i's are the eigenvalues of a particular matrix. Eigenvalues of this particular matrix in descending order. And sigma y is the polymatrix, this particular polymatrix. And this symbol over here is the tensor product. So tensor product of sigma y with itself is the following. So how we evaluate the tensor product? So what we do is, this element multiplied with the entire matrix, then this element multiplied with the entire matrix, similarly this element multiplied with the entire matrix, and this element multiplied with this entire matrix. So 0 times this is 0, so that's why this part is 0. So this part, then minus I times this matrix. So minus I times minus I is minus 1, minus I times I is plus 1. So this part comes from here. Then I times this matrix. So this part comes from that, and then 0 times the matrix. So this is that. So that's how you evaluate tensor product. Now we need to look at this matrix. So rho is this, Now let us multiply. So this with this let us multiply, and then this with this let us multiply and see what's the result. Now let us multiply these. So this is the final result. Now we can further simplify by making use of this thing C equals D star. So this will give me now eigenvalues of this above matrix we need to find out. So eigenvalue of a matrix, if this is the matrix A, then eigenvalues is given by determinant of A minus lambda I equals 0. This basically gives the eigenvalues. So, and we will make we will expand by the top row, and these two are the non-zero elements of the top row. We will expand from that. So when you add this minus lambda I, so what you will get is you will get minus lambda, minus lambda, minus lambda, and minus lambda. And then expanding by this 2AC. So from this part we get lambda 3 equals lambda 4 equals 0. Why lambda 3, lambda 4? Because these are 0 and descending order we will write. So lambda 1 and lambda 2 will be greater than 0. That's why. Now let us look at this term. And since C equals D star equals C, this is basically mod C squared. So using the quadratic formula, this gives us the following for lambda. Now let us open up the brackets. So certain terms cancel out. So this gives me lambda 1 equals the following. And lambda 2 as the following. Again, because we have to maintain descending order. Now we can find out the concurrence. And these are 0. Square root of lambda 1, just the square will go away, so mod a plus root ab plus mod c minus square root of lambda 2 again. And of course 2 mod c will be greater than equal to 0. So this maximum is 2 mod c, which is 2 k1 k2 w. This we had seen in part B, that c is this k1 k2 w. Here we are making use of that from part B. So this completes part C, where we found the concurrence. Okay, so next question, part D, find the visibility. So visibility, the definition is given as follows. Max minus min of the coincidence count probability over max plus min. And RSI, we are already given the expression. Now maximum will occur when this so everything maximum or minimum will actually depend on this cosine term. So when cosine term is 1, then we get maximum. When it is negative 1, we get minimum. So using this, we get the visibility. Sorry, there is a 2 over here and a 2 over here. So this 2 cancels with this 4 over here to give a 2 in the numerator. Now this root s2 rho 1 s2 rho 2 times mu is actually w. So this is 2 k1 k2. This is proportional to concurrence. And how we can see from this part, we saw this concurrence is equal to 2 k1 k2 w, and we have that same term over here in the numerator and an additional term in the denominator. That's why it is proportional. Okay, next part. What is concurrence when A equals P and mod C equals mod D equals half? Let us see that now. So A equals B, mod C equals mod D equals half. This gives concurrence equals 1, because concurrence is 2 mod C from part C, and if mod C is half, then 2 into half gives us 1. So this means that state is maximally entangled. And then how do we achieve this? So A equals B. So A is what, B is what we saw here, A and B. So these represent the probability of the two photons being in alternative 1 and alternative 2 respectively. So if these probabilities of the two photon alternatives are made the same, that same probability for going in alternative 1 and same probability for going in alternative 2, that will make A equals B. Then now part F, the last part for this question. What is concurrence when A equals B and mod C equals mod D equals 0? In this case, the concurrence will be 0, because concurrence is 2 mod C and mod C is 0, so concurrence is 0. So this means state is not entangled. Not entangled or separable. And how do we achieve this? We get this by making the alternatives distinguishable. So once they are distinguishable, then you will get separable. And in that case, mod C will be 0. Okay, so this completes question 1. Take a few minutes to just recapitulate what we did over here. There were a lot of parts involved. We mainly found concurrence and the method for finding concurrence. Okay, so let me see if there are any questions in the chat box before proceeding. Seems like there are no questions. Okay, so we can proceed. But I see that we are running short on time and we have this problem 2 which has got 4 parts remaining. So maybe we can take it up in the next class. Maybe I can just read out the question. This is on polarization. So right now we discussed spatial 2 photon state. Now this is polarization 2 photon state. Let me just read the question and then we will discuss in the next class. So this is problem 2. Consider a 2 particle state psi 1 equals A HH plus B VV, where A and B are real numbers and where A squared plus B squared equals 1. This is for the normalization condition. Consider another 2 particle state psi 2 equals PHV plus QVH, where again P and Q are real and P squared plus Q squared equals 1, which is the normalization condition. Write down the density matrix rho 1 corresponding to the state psi 1. Calculate the concurrence. Once again concurrence. We just now saw how to find concurrence. Now consider a 2 particle state that is an incoherent mixture of the states psi 1 and psi 2 with equal proportion. Write down the density matrix rho for the state and again find out the concurrence. So concurrence, how to find out, we just saw in this particular part C. So concurrence is given by this particular expression where these lambda i's are the eigenvalues of this matrix, where rho is the given state and sigma y is the this particular poly matrix. And we will take it up next week. So 10 weeks are complete, 2 more weeks to go, and then there will be one revision video. Okay, so that's all from my end for today's lecture. We will meet again next Saturday at 3 p.m. So if you have some questions, feel free to ask by unmuting yourself or in the chat box. If not, then please log out from the Zoom meeting. Yeah, bye bye. See you next week. Okay, once again, someone is asking where's the Zoom link for this course. So let me put it up in the chat box. Let me copy. Yeah, so that's that. So I've put up the link to the YouTube channel for this course. This is the channel where I post these weekly live problem solving sessions. Every week the video is uploaded over there, so if you happen to miss one live session, you can actually go back to the channel and watch the video. And if you have some queries whenever you are studying and you want to revise, you can again go to the particular video and watch it again at your own convenient time. Okay, so seems like no more queries. So people, please log out from the Zoom meeting. We will meet next week now. Thank you very much.